Alright, so we might remember from single variable calculus the idea of a derivative, and the idea of a derivative being represented kind of as the following, where we have dy over dx, almost got the formula wrong, and that would be equal to f prime of x. Alright, well, we could possibly take this a step further, this idea a step further, and we could say dy is equal to f prime of x dx. And so this is where kind of the idea of what I like to call a differential comes into play. And the whole idea of a differential is that we could approximate a certain value for f of x, and this gets into a lot of linear approximation stuff. And if you haven't watched our linear video on linear approximation, I highly suggest you watch that first. And so this whole idea of a differential can kind of translate over to multivariable calculus with the idea of what we like to call a total differential. And we essentially take this very concept and we introduce the idea of partial derivatives, and we use that to define a total differential. And so a total differential in the context of multivariable calc is essentially the following. We have we have dz, which is basically what our function is being defined as, and so where z is what our function is being defined as. And then we basically take the partial derivative, and these are just sample variables here, but we take the partial derivative of z with respect to x multiplied by dx plus the partial derivative of z with respect to y multiplied by dy. And that kind of is essentially the formula for a total differential. I'm going to write that. The general equation, I would rather say general equation for total differential. Alright, so we're going to keep it at that. And we can do this for any number of variables. If it had, 15 variables, then we can take the partial derivative of those variables multiplied by the differential and then continuously keep on adding them together. And so that is kind of, we've kind of strictly thought of this in terms of 3 variables, x, y, and z, but this could be for any number of variables. And so, like I said, we're essentially extending the concept from we're extending the concept from single variable calc, where we're taking the differential of just one variable and we're doing it for multiple variables. And so that's kind of the idea here, taking the partial derivatives, multiplying them by d of x or d of y, and we're calculating a total differential. What might this look like in practice? Well, we can actually bring out a graph here, so give me a second. And so this is what the graph might look like of any given function. And for example, we might have a point defined somewhere, and it doesn't really matter where, but we might have a point given here, for example. Oops, that's not that great of a point. Right over there. And we might have a tangent plane somewhere, and that tangent plane, and I used yellow previously, so we might have a tangent plane that's defined somewhere around here like this. I'm going to do my best to draw the best tangent plane possible. Yeah, that looks pretty good. I'm going to keep on bringing it down from here across. I'm just going to kind of shade it in a little bit. Alright, and so we have a tangent plane, and we can imagine that that tangent plane is kind of extending. And we might say, for example, that the change in the value from one point to a second point, and let's define a second point. So we have a first point over here. A second point, for example, might lie somewhere over here, and its respective point on the tangent plane, or its respective approximation on the tangent plane, might be somewhere around here. It doesn't really matter where. What we're trying to get at is that the change in the value of z might be defined as delta z, and that's going to be from here to here, and that's delta z. And then the change in the value of the differential, the total differential, might be defined as the change in the value in the tangent plane, and that's going to be dz right over there. And so just to reiterate, dz represents the change in height of the tangent plane, whereas delta z represents the change in height of the surface, where this surface is actually z equals f of xy. Let me write that down. So this is z equals f of xy. So we have delta z being the change in z, whereas dz being the change in the height at the tangent plane. And so these problems are very simple, actually, if you really think about them. We've already learned about partial derivatives. If you haven't, once again, go check out the video. Well, we already know about partial derivatives, and we're essentially going to take that concept and extend it over, and we're going to say that dz is going to be equal to the partial derivative with respect to z with partial derivative with respect to any given variable multiplied by the differential of that variable. We're going to continuously keep on adding that, and then hopefully we can get a total differential. And also, we also have this kind of idea where we can represent dz as kind of an, dx or dy as kind of an approximation. And so we might actually be able to say that, hey, look, we have, for example, dx. Whoops, let me get into pen mode. We might have dx, for example, and that can be equivalent, or at least somewhat equivalent, to delta x. And that, we already know that delta x is basically the change between 2 points. And so we can call that x minus a, for example. And so once that happens, then we can kind of redefine the whole idea of a differential to be dz is equal to the partial derivative of z with respect to x multiplied by x minus a, or the change in the value of a. And then we can similarly do that for y, and we can do that for any number of variables. We basically take z with respect to any given variable, multiply that by the change in the value of that variable. Now let me do b for that. And so that is kind of the whole idea of a differential. And we can, we'll be getting into some examples to show you what an actual multivariable calc problem might look like when we're talking about differentials. Alright, we are asked to find the differential of the following function, the function being f of, is equal to y over 1 plus x, y, z. Alright, so first things first, we're going to have to take the partial derivative of f with respect to each one of these variables, x, y, and z. So let me first rewrite this to actually be much easier for us. I want to remove the fraction, it's much easier that way, and so now we can actually deal with each of the variables a little bit more in a better way. So first off, let's do the partial derivative of f with respect to x. So partial derivative of f with respect to x. First things first, we're treating this y as a constant. We completely ignore it. We go to the x containing term over here, and over here treating both y and z as a constant. I know that the derivative of this is essentially going to be just yz, because yz is a constant and x is not. And so using the idea of the derivative, we can just basically just take out this x, and so we have yz. And but before even all of that, we actually have to take down this -1 and then change it to -2 as a result of the power rule. And so what we get as a result of all of that is we get -2y squared z over 1 plus x, y, z squared. Again, let me just reiterate what we did. Actually, sorry, this is not supposed to be -2, it's just supposed to be negative. Yeah, that was my bad. However, what we essentially just did is we took down this negative over here, we changed it to -2, and then we took the derivative of the following term, treating both y and z as a constant, and we got yz, and we took that out, and we brought it back out into the numerator, and so that's what our resulting function looks like. Alright, for the second partial derivative, which is the partial derivative of f with respect to y. Okay, so we're clearly going to have to use product rule over here because we have two y containing terms over here. Let's do the easiest one, which is just going to be the y, and so that's going to be the derivative of y is just going to be 1. And so we're left with 1 plus x, y, z to the power of -1, added to, again, we're doing the same exact thing as we did earlier, except this time we're turning both x and z as a constant. In doing so, we get negative, once again, we change that to -2, and then we bring x and z out onto the numerator, and so we get negative x, y, z, all of that over 1 plus x, y, z squared. Alright, we can simplify this if we wanted to, and actually I'm going to do that right now. We changed the 1 over 1 plus x, y, z to 1 plus x, y, z over 1 plus x, y, z squared. I apologize for the bad handwriting. Subtracted by x, y, z over 1 plus x, y, z squared. And that, well, these two x, y, z cancel out, and so we get essentially 1 over 1 plus, 1 plus x, y, z squared. Alright, final partial derivative, which is going to be f with respect to y. And so let me write that down. So we have the partial derivative of f with respect to y, or sorry, f with respect to z, I apologize. If you remember from the previous function that we had defined, let me bring that up real quick. We're treating this y as a constant. We're treating x and y also as a constant in this term over here. We're basically doing the exact same thing we did earlier. In fact, let me just copy and paste this. Copy and paste this. Bring it down. And now we don't need this. And we're basically going to be doing the exact same thing, almost the exact same thing as we did earlier. Except what we're going to do is we're finding the partial derivative, of course, of f with respect to z. So the first thing we're going to do is change that. Second thing we're going to do is we're going to replace what we're taking out from this term over here. What we're taking out is going to be x and y. And so what that results in is not z over here, but instead an x. And so we can essentially just replace this with xy squared. And so what that looks like is the following. Let me reiterate what I just did. We brought down the negative because of power rule. We kept the y at front and constant. We brought down the negative, changed the power to 2, and then we were also taking out x and y from the derivative of here because we're treating x and y as constants. We bring that up to the numerator, multiply that by the y, we get xy squared, all of that over 1 plus xyz squared. And we also have a negative. Alright, so we have all of our partial derivatives. Now to find the total differential, which is what the original question was asking for originally, we have to remember kind of these partials over here. Let me copy and paste the partials that we had defined for each of the variables. So first, we're trying to find the partial, so let me define partial as dz is equal to negative y squared z over 1 plus xy squared. That's going to be multiplied by dx plus 1 over 1 plus xyz squared multiplied by dy, because that is the partial derivative of f with respect to y, minus xy squared, xy squared over 1 plus xy squared, or xyz squared. And that's going to be multiplied by dz, because again, that is the partial derivative of f with respect to z. And so that is our total differential. This should not be the partial derivative dz, instead it should be df. So again, that is our partial derivative, or total differential. And so again, what we did is we found all of our partial derivatives, multiplied them by dx or dy or dz, and then that is how we're defining df, aka our total differential. And thus that is the answer to this problem. Let us look at another example of total differentiation. Alright, we're asked if z is equal to 5x squared plus y squared and xy changes from 1.2 to 1.05 to 2.1, compare the values of delta z and dz. Alright, so first things we're going to have to do is find the dz, which is aka the total differential. And so the first step is obviously finding our partial derivatives. It all starts out with partial derivatives. So first things first, the partial derivative of z with respect to x. Treating y as a constant, this is very easy, it's just 10x. Then we have the partial derivative of z with respect to y. Again, very easy. This is just going to be 2y because x is a constant and it becomes 0. Alright, so we have the partial derivatives, and now we're going to find our total differential. And so our total differential, dz, is going to be equal to 10x dx plus 2y dy. We would be done with this problem if this is only asking us for the total differential, but it's not. It's asking us to compare the values of delta z and dz, given the fact that xy changes from one point to another. Alright, so in order to do this, and sorry, I forgot to write the x over here. So in order to do this, what we first need to do is sub in these values and find the value of the differential, and then also find the value, the change in z. Alright, so let's first do the differential because that's probably going to be the easiest. So first, I'm going to do dz from 1.2 to 1.05, 2.1. Well, that's going to be equivalent to 10x, and what is our original value of x? Well, the original value is just going to be 1, so we have 1. What is the change in x? Because we're treating dx as the change in x, so the change in x is just going to be 0.05, because 1.05 minus 1 is 0.05. And then we can do the same thing for y. So plus 2 in our y, the original y is 2. and the change in y is 0.1. 0.1. And so we compute this. It ends up being 10 times 0.05, which is 0.5. And then we also have that being added to 0.4. And so the total differential at those 2 points is going to be 0.9. Okay? Whoops, we're not going to box that because we're not done yet, because now we have to find the change in z and compare those two values. So the change in z, given that z is equal to 5x squared plus y squared, the change in z is simply going to be equal to 5x squared, 5 times 1.05 plus 2 times 2.1, or sorry, not 2 times, we're just simply going to do 2.1 squared, minus 5 times 1 squared plus 2 squared. And so we're basically, in order to find the change, we're subbing in the values, the later values subtracted from the original values, being subtracted by the original values. And so we're actually going to have to compute this using a calculator, because I don't know what 1.05 squared is off the top of my head. And so using a calculator, we can say that the value of this is equivalent to just about 0.9225. Alright, so now we can compare these two values, and that is essentially what the question is asking us to do. Is we're going to take this value of dz and compare it to dz, or sorry, delta z. So we're comparing those two values. What do we see? They're awfully similar, and that is kind of the idea behind this whole differential, is that the total differential is essentially kind of an approximation of delta z. Now, if we had a very large difference between the original x and the new x, then obviously that won't be the case. But clearly, we see a very nominal change in what dz is and what delta z is, and it's about 0.0225. And so we can say they're not awfully that far apart in terms of values. Now we can look at a final word problem example, which is an application of differentials. Alright, so we're asked that the radius of a right circular cylinder is measured as 2.5 feet, and the height is measured as 12 feet. And suppose that each measurement has a possible error of at most epsilon feet. Now use the differentials, this is part A, use the differentials to estimate the maximum error in the calculated volume of the cylinder. And then part B says that if the computed volume must be accurate to within 1 cubic feet, determine the largest allowable volume of epsilon, or value of epsilon. So I prefer to draw a cylinder, a diagram of a cylinder for the purposes of this question. And so we have a cylinder. It's going to look something like this. And as we already know, cylinder has a given radius. Let me draw that radius. And it's going to have a given height. It's going to look something like that. And so, in order to calculate first our total differential for this problem, we first need to understand what kind of formula we're going to be working with here. And so I can very clearly see we're working with the formula for volume, and the volume we already know for a cylinder is going to be pi r squared times h. Very self-explanatory stuff. Volume is going to be equal to pi r squared times h. In order to calculate our total differential, we first need to find our partial derivatives of v, volume, with respect to both radius and height. So del v over del r, so the partial derivative of v with respect to r, well, that's just going to be 2 pi rh. Treating pi and h, pi is already a constant, but treating both pi and h as constants, we know that the derivative of r squared is going to be 2r, so our partial derivative of v with respect to r is going to be 2 pi rh. And then the partial derivative with respect to h is just going to be pi r squared. And that's just because when we're treating h as a changing variable and pi r squared is constant, it's just going to be pi r squared. And so now let's construct our total differential, right? And we're using epsilon as our error. And so using epsilon as our error, in order to calculate our total differential, we're going to have dv, and that's going to be equal to 2 pi rh times epsilon, and then that's going to be added to pi r squared times epsilon. And so we have our two errors over there, we have our partial derivatives, that's summing those two together, that's going to equal our total differential. And now to find the total differential, To estimate our maximum error in the volume of the cylinder, all we need to do is substitute in the given values that we have, and we're given that the radius is 2.5 feet and the height is 12 feet, and so in that case, the differential when radius is equal to 2.5 and height is equal to 12, well, we just need to sum in these values. So let's first sum in these values. So we have 2 pi times h, which is 12, or sorry, r, let's first do r actually. So 2.5 pi, or sorry, 2 pi times 2.5, that was a mouthful, times 12, which is h, is going to be multiplied by our error, which we're going to set as just epsilon. We're going to calculate epsilon later, and so, or sorry, calculate our total differential later based on epsilon, and so that's going to be added to pi times r squared. R is going to be 2.5 squared, and by the way, we should probably already know that 2.5 squared is going to be 6.25. I'm going to keep that in the back of my head, that 2.5 squared is 6.25, and that's going to be multiplied yet again by epsilon. Again, we're answering this question in terms of epsilon. Okay, and so all we have to do now is just evaluate this. This is simple algebra, and so we're going to have is 60 pi epsilon plus 6.25 epsilon, and that's pi, sorry, I forgot that pi over there, pi epsilon, and that's just going to equal 66.25 pi epsilon, as such. And that is going to be our maximum error. So this is the answer to part A. This is the answer to part A. Now for part B, what we're going to have to do is that we know what the maximum error is going to be, right? We know the maximum error is going to be 66.25 pi epsilon. And so now we just need to find what that epsilon value is going to be. Because what is the question asking? The question is asking what is the largest allowable value of epsilon? And so we know that it needs to be accurate within 1 cubic foot. We know that this value essentially needs to be, and this is for part B, so 66.25 pi epsilon, that value needs to be less than or equal to, it depends on the context of the question. So let's go back to the question real quick. It needs to be accurate to within 1 cubic foot, so we have less than or equal to, and that's going to be less than or equal to 1. And so epsilon must be less than or equal to 1 over 66.25 pi, and that is essentially equivalent to 0.058 inches. And so that is going to be our maximum allowable value of epsilon. I'll be posting the PDF version of this whiteboard onto the description of the video. Thanks so much for watching. If you have any questions, feel free to leave them in the comments. Otherwise, once again, thank you so much for watching, and yeah.